Okay, well, we got to this point yesterday talking about the definition of the definite integral and all the little details leading up to this part, and basically writing up the Riemann sum, how we got all these little parts, and the 2 over n and the 2i over n, and plug that into our function. So today we're going to take it that next step and actually evaluate this limit. So as we look at what we have here, we are really going to need to rewrite the form of the summation into something that we can calculate. Now, before we do that, let's look at our limit. We really don't have anything in our limit that we're trying to calculate that deals with the delta or the mesh. But think about the meaning of that. We're going to convert this into a limit dealing with n. So we have said that delta x is 2 over n. Now we're saying, this notation, we're saying the largest one of these delta x's, which we have said they're all going to be the same. So this is going to approach 0. So 2 over n approaches 0. Okay. Now, in practical terms for what we can use, we want to say, well, what about n? What's n doing if 2 over n approaches 0? N is approaching infinity. As 2 over n approaches 0, that means n has to be approaching infinity. Okay? So right there we can change the form of our limit. Instead of looking at that really technical notation, we can make it something we've dealt with before. As the mesh approaches 0, then n is approaching infinity, and now we can work on that. Now, we have the summation. We can do a few things with this to make the notation a little bit easier. First of all, we're saying the summation as I equals 1 to n. So the summation is going to involve the I. 2 over n, this factor right here, well, we can kind of think of that as it's going to be multiplied by every term, so we can factor it out. Okay? So we can say 2 over n times this summation because the 2 over n is going to be 2 over n for every term because it's the I that's changing, not the n. So now, let's see what we need to do here. Cubing 2i over n, we have to cube every part of that. 2 cubed would be 8. I cubed, and then over n cubed, and then plus 1. Now, getting too many grouping symbols here, we'll introduce that as our grouping symbol. Actually, I drew that pretty good. I usually don't use the brace because I can't draw it. But. Now, let's see what we can do with this. Kind of introduce or review, remind you of some of the summation properties. Some of you have worked with summation before, some of you never have. So, like I said, either introduce or review. Summing 2 terms here, think about summation. We're adding a whole bunch of terms, well, adding and then adding each part. Addition is commutative, so we can rearrange the terms and we can separate this into two different summations. We can say the summation of the 2 over n out here is times everything that's left. But we can say the summation of 8i cubed over n cubed plus the summation of 1. Okay. And then, like we saw with the 2 over n, we factored it out. We can make this one a little bit nicer by factoring the 8 over n cubed out of it. And we'll end up with the limit as n approaches infinity of 2 over n times eight over n cubed times the summation of I cubed from 1 to n plus the summation of 1 as I goes from 1 to n. Okay. Questions up to that point? Okay. Some of the questions that you have, very good questions, kind of the properties of these summations. And if we see something like this, the term is I plus 1. Now let's go ahead and write out in the form of I plus 1, in that binomial form, for I going from 1 to 5. So when I is 1, we would have that. When I is 2, we would have that. 3, 4, and 5. Now, from there we can simplify. We can regroup each one of those terms. We added 1. So instead of writing out I plus 1 each time, we can separate it and say it's the same as the sum of I plus the sum of 1. Now we need that 1 in there because notice it shows up every time. It doesn't change. There's not an I in that term, but it still counts as part of the summation. And this even kind of leads to the properties of summation. So when we separate it out like this, we can write out, of course, 1 plus 2 plus 3 plus 4 plus 5. That would be the summation of I from 1 to 5. And then plus, well, summation of 1 from 1 to 5. When I is 1, well, 1 is going to be 1. When I is 2, 1 is going to be 1. And ultimately, we end up with that, which again, it's the same summation, but we're using the properties to rearrange terms. Commutative property, we can do that. Now, notice, what do we get here? Okay. Or this really is the definition of multiply. We're taking 1 5 times and we get the value of 5.
This is where we get multiplication from?
Yeah.
That's pretty cool.
The summation of, let's say, 3, and let's go from 1 to 4. Okay. Well, in summation form, we'd have 3 plus 3 plus 3 plus 3. Repeated addition is the definition of multiplication. We have 3 4 times. Well, if you need to get your calculator out, this would be 12, and so is this. That's why we can learn that 3 times 4 is 12, is because it is the sum of 4 3s.
That's pretty cool.
So for the summation properties then, this will be kind of our first, I guess, our most basic property. I guess this we showed here was a property, but it's pretty straightforward. What we're going to show for formulas is dealing with this, the 3, and then we can say that's like our n. The summation of a constant from 1 to n is going to be that constant times n. Okay. And we can also show a formula for the summation of I, for I squared, for I cubed. There's a lot of summation formulas. We're only going to use a few of them. But here is the formulas that we will be. Like I said, summation of a constant is that constant times n. Summation of I, as I goes from 1 to n. Well, we had 1 plus 2 plus 3 plus 4 plus 5. Let's just verify that this works. That's what? 15? Should I check him? Well, in this formula, n is 5. N times n plus 1 over 2 equals 15. Okay. Now, I squared gets a little more complicated, but again, the formula here. Now, this is what we'll be using in our definition of the definite integral. Okay.
Well, how do you do the division? How did they figure out division?
You have to prove it.
Yeah, you'd have to prove it. But all we're going to deal with for these summation formulas are these 4. There's tons and tons of others, but this will get the point. And in fact, we won't use I cubed very much, but our previous example has an I cubed in it, so we need to include that. Okay? Okay, so let's take a look at how we would use this. Keep this one in mind. That's what we'll need to do to finish up our problem. So now with these formulas, we're going to be able to change the summation terms into terms of n and ultimately be able to calculate this limit. Okay. Well, we do have the summation of I cubed. So that summation formula was what?
N squared times n plus 1 squared and then over 4.
Okay, so that right there. Now, we didn't prove that formula. There is a proof, but it gets rather lengthy. I'm not going to do that right now. But that will turn into this right here. And now that particular summation was multiplied by 8 over n cubed. So we've got that. And then the whole thing was multiplied by 2 over n. That one as well as this summation. So the summation of 1 as I goes from 1 to n could be written as what?
N.
Okay, that's going to be your constant times n. Well, the constant this time is just 1, so that summation is going to be n. Okay. Now, that's more or less the algebra of it. We still need to take the limit. Well, there's still some algebra we need to do to get it to where we can take the limit. Okay. Questions up to this point? Well, from here, let's see. We've got lots of algebra, lots of directions we could go. To make sure we don't lose this one, let's go ahead and multiply it through, which would be 2 over n times the 8 over n cubed. Give us 16 over n to the 4th, which is multiplied by this. And then my favorite mistake is forgetting about this times this one. Oh, 2 over n times n will leave us with just 2 on the very last term.
Because it's 2 over n.
Okay, this times all of that quantity.
Would it be 2 over n?
2 over n times n. The n's would cancel.
Oh, yeah.
Okay. Okay, so we still have quite a bit to do right here. We can at least look at the constant. 16 divided by 4 would leave us with 4 in the numerator. And let's see, this n squared times n plus 1 squared. Let's go ahead and multiply that out. N plus 1 squared is what?
N squared plus 2n plus 1.
And then ultimately our numerator, well, we could put the 4 in there as well.
Couldn't we just cancel out the n squared and then 4 at the beginning?
Yeah, we could do that. Algebra-wise, there's a lot of different directions. So at this point, let's go ahead and put all of this back into that fraction. We'll have the 4 n squared plus 2n plus 1. All of that will be over, all that's left in the denominator is n to the 4th. And then we don't forget about that one. That's still part of our limit. We haven't done anything with that yet. But that will end up being part of the answer. And then, as Stephen said, n squared divided by n to the 4th, that'll cancel to n squared in the denominator. And then, well, probably the next easiest thing to do is simplify this, separate this into 3 different fractions. We're almost there. Once again, it's the algebra that's the pain in the,
Yeah.
well, yeah. So separating out
Oh, shoot.
those fractions, and then we still have plus 2. Okay. And as we simplify, this will end up being 1. We'd have 2 over n, and I guess that one's not going to simplify at all. Okay, let me translate that to the top of the next page. So, as we finally apply the limit, well, the limit of a constant is what? That constant. The limit of 2 over n as n approaches infinity.
It gets smaller.
Okay, that part will go to 0. 1 over n squared as n approaches infinity.
0.
Also 0. And again, the limit of a constant, no matter what n goes to, is going to be that constant. So all of that simplifies to, well, 6.
This key seems cold.
What the?
Anticlimactic, isn't it? Now, remember where we came from. This was our original problem, definite integral from 0 to 2 of x cubed plus 1 dx. That equals 6.
Oh my god.
So the integral is gonna equal 6.
Yes, the integral is going to equal 6.
There's-
Now, how we've developed that, this 6 represents the area under this curve from 0 to 2.
Exactly.
Exactly. That is the exact area. Remember all the approximations we did? First one, n equal 4. Left endpoints was 4.25. The right endpoints was 8.25. N equals 8. Did we actually calculate that one?
Yeah, it was like 6.25.
I don't know.
We got the left.
Yeah, we did one part, but, well, guess what? This part would be probably 5.8, 5.7, something in that neighborhood. And again, it's showing we're getting closer to the exact value. And as we get more and more rectangles, we get closer and closer with the approximation. And ultimately, to get the exact area, we have to go with an infinite number of rectangles, which brings in our limit as n approaches infinity. Okay? Okay. So now you're going to be able to do the full, calculate the definite integral using the definition of the definite integral. Now, I've given you only 4 problems on that worksheet, but they'll take you a little while. And then tomorrow we'll see a nice little shortcut that make this much easier. But for now, we're ready to use that definition.